Hello, everyone. This is Adnan. Welcome to Chemistry with Adnan. This is another lesson in the series where we are covering the entire GCSE Cambridge Chemistry 0620 syllabus. I also offer online lessons one-to-one. The Google form is given in the description. And you can also join my community, High School Chemistry, on school.com. And the link is given in the description where I offer one lesson per month, which is free, and you can also join my premium package where I offer 4 lessons a month, and you can also ask me questions. And it's a fun place to be. There are some group discussions as well. You can also meet other students from all around the globe which are studying chemistry. So okay, so now let us begin. In this lesson, we will be covering 2.6 giant covalent structures. So in our previous lesson, I introduced what giant covalent structures are while I was explaining simple molecular structures. So I had to talk about giant covalent structures so that you can understand what giant simple covalent structures are, much better. But in this lesson, we will be talking about giant covalent structures in more detail. So you at this point, you may already know, if you are watching the entire series, starting from lesson 1, that what giant covalent structures are. So giant covalent molecules or giant covalent structures are those structures or molecules where there's a covalent bonding between the two molecules, right? So for example, this is one molecule, silicon 4 oxide, and it is also called silicon dioxide, and this is another silicon dioxide molecule. So there will be a covalent bond. So these two molecules, these two compounds will be connected by a covalent bond, right? So and so they are connected in a network. They form a crystal lattice sort of structure, just like we see in ionic compounds. But the only difference is that in ionic compounds, the crystal lattice contains ions, negative and positive, cations and anions. But here we don't have any ions, as they are held together by covalent bonds. Electrons are shared between these atoms. So we will be looking at these structures in much more detail here. So now let us start topic number 1, which states that describe the giant covalent structures of graphite and diamond. Yeah, so what you need to know that in each of these, what is the pattern of connectivity? What do I mean by pattern of connectivity? That let us talk about diamond first. So in diamond, what you need to know is that each carbon atom is connected to 4 other carbon atoms: 1, 2, 3, and 4, right? And the name of the geometry, it is called a tetrahedral, right? So this is a tetrahedral 3D shape. And a diamond is very hard due to many strong covalent bonds. So if I quickly draw the structure here, so it looks something like this. I hope I'm able to draw this accurately. Yeah, so these bonds, yeah, they something, they look something like this. So this is a tetrahedral geometry, and diamonds, they don't conduct electricity because there are no delocalized electrons. So I've explained in my previous lesson as well that why molecules or atoms, they can conduct electricity. It is because the delocalized electrons or ions, they can move. And here we don't have any delocalized electrons, so diamond, it does not conduct electricity. So now we move on to the structure of graphite. So graphite is basically the both diamond and graphite, they are allotropes of carbon. What are allotropes? These are the same elements, but they are found in different structural forms, right? So same element, a different structural form, that is an allotrope. Do not confuse it with an isotope. Isotope is entirely different. Isotope is the same proton number but different neutron number. In this case, their structure is different. We are talking about their macro property. So graphite, what you need to, again, the pattern of connectivity between the carbon atoms will be in graphite. So each carbon atom is connected to three other carbon atoms. So this is the difference between carbon and diamond and graphite. Diamond is connected, in diamond each carbon atom is connected to four other carbon atoms, but in graphite each carbon atom is connected to three other carbon atoms, right? So and its structure consists of layers of hexagonal rings. So this is also very important, you need to remember this: layers of hexagonal rings, right? And with no covalent bonds, with no covalent bonds between the layers, right? Between the layers. Okay, so it looks something like this. Hexagon means six rings, so six atoms, one or rings with six corners, 1, 2, 3, 4, 5, and 6, and then like this, and like this. Yeah, and this is one layer, and then we will have another layer, but there will be no covalent bonding in these layers. We have weak forces of attraction, we have weak intermolecular forces between these layers, right? So we will talk about the significance of this in our upcoming topics, which is topic number 2, that why this property, or how this property makes graphite a much useful substance. Okay, so this is basically this is how the structure of graphite looks like. And again, I will repeat, what you need to remember is that the pattern of connectivity, that each carbon atom is bonded to three other carbon atoms in graphite, and in diamond each carbon atom, it is connected to four other carbon atoms, right? So now we move on to the second topic, which states that relate the structures and bonding of graphite and diamond to their uses, limited to graphite as a lubricant and as an electrode, and diamond in cutting tool. Okay, so graphite as a lubricant. So now this is what I was referring to, because these layers, as they are not held by strong covalent bonds. We have weak intermolecular forces here. We have weak intermolecular forces between these layers. So that is why when a force is applied, these layers can slide, right? These layers can slide, and this makes graphite a lubricant. Why? Because since the layers are connected by weak intermolecular forces, meaning the layers can slide over each other, resulting in graphite being soft. So this is what you need to know. And for diamond, it is the hardest substance, natural substance known, because of its tetrahedral geometry. and so many strong covalent bonds. It is used to cut stones, cut marble, and different types of things. So just because its extreme hardness, it can be used in it can be used as a cutting tool. Right? It is used in drilling machines and stuff like that. So this was our topic number two. So one thing I would like to add here. Let me see that if they talk about that in our no, they don't. Okay, so this is important. I have to talk about this. So since like we have studied in our previous lessons that a carbon atom, it has 4 electrons in its outer shell. So here, since carbon atom is bonded to 3 other carbon atoms, it means that 1 electron in each carbon atom, it will be delocalized. It is not involved in chemical bonding, and it gets delocalized, and that is why graphite is one of the very few examples where a non-metal can conduct electricity, right? So this is a special structure of carbon, an allotrope of carbon, in which carbon is bonded to only 3 other carbon atoms. So each electron, like 1 electron in each carbon atom, is delocalized, it is free, and that is why it can conduct electricity. So this is what you need to keep in mind, right? So now we move on to the uh, extended section, supplement topics. Describe the giant covalent structure of silicon 4 oxide. So I've introduced this molecule in our previous lesson, and at the beginning of this lesson as well. So now here we also need to know that how what is the pattern of bonding. So silicon dioxide, it is also known as silica, which is the main component of sand. So when you go to the beach next time, and the sand beneath your feet, just remember that it is mostly silica. So the formula is SiO₂. So each silicon atom is covalently bonded to 4 oxygen atoms, right? So here, like this, right? And yeah, so again, like, you just have to complete the chain, right? Each silicon atom must be connected to 4 oxygen atoms, right? So this is basic, and these are this is a giant covalent structure, network covalent bonding. And yeah, uh, that this is why it will also have very high melting and boiling points. So both like diamond and silicon dioxide, they have strong covalent bonds which require a lot of energy to break. So both diamond and silicon, they have high melting and boiling points, and both diamond and silicon dioxide, they have their atoms bonded in a tetrahedral arrangement, which means both structures are very hard and rigid. So this was about the giant covalent structures. So give me a second, let me paste a few questions from the past papers, so that you can see that what type of questions are generally asked about these topics here. So, uh, okay, yeah. So we have a question here. Let me just quickly paste it. Okay, we have one more topic to cover. So, okay, let me show you this question, because this is related to the stuff that we have already covered. So I'll explain this topic number 4 in a few minutes after discussing this. Okay, so now the first question, it says that state the type of bonding in state the type of bonding in graphite. So this is an easy question from paper 3, I believe. So this is covalent bonding. So we write covalent here and you get 1 mark. Explain by referring to figure 8.2. Yeah. why graphite is used as a lubricant. Yeah, you see, this is the exact thing that I just explained. That since we have weak intermolecular forces of attraction, so the layers can slide, right? So how will you answer this question? You will say that the layers can slide over each other, right? Yeah. So this is going to get you uh, another mark. Next question: graphite and diamond are both forms of carbon. State one use of carbon. Yeah. So you can say that it can be used as a cutting tool, right? So you can write here cutting tool. So you don't have to explain that why it is used as a cutting tool. They are just asking you about the use, right? You don't have to justify or explain that why it is used as a cutting tool. So uh, and so this is how basically these are the type of questions that you will be asked on the exam. So now we go to the final subtopic of this lesson. Oh, let me just change this here. 2.6. We are learning about giant covalent structures. Okay, so yeah, describe the similarity in properties between diamond and silicon oxide related to their structures. Okay, I think while solving this, yeah, I think I mentioned it in while discussing this the other part. Yeah, so same thing, same pattern. In diamond, carbon is connected to four other carbon atoms, and in silicon dioxide, silicon is oh, this is Si. Silicon is bonded to four carbon oxygen atoms, and they both have tetrahedral structures, and they are very hard. And diamond is harder than silicon dioxide, but yeah, they both of them, they are extremely hard substances. So this will be all for this lesson. And if you have any questions, you can leave them in the comments below. And yeah, again, a reminder to join my community, High School Chemistry, on school.com. And if you need one-on-one lessons, so better book early so that you don't miss this chance. Okay, so this will be all for today. I'll see you in the next lesson. Take care. Goodbye.